So last time we talked about square root functions, and now we're talking about cube root functions. Everything that we said about translations, reflections, and dilations for square root functions holds true for cube root transformations. So we can move the function up or down by adding a constant value to it, or we can move it left or right by subtracting a constant value from the x term. We could also reflect it across the x-axis by multiplying the whole function by a -1, or we could reflect it across the y-axis by multiplying x by -1. Vertical stretches and compressions work the same as well. So if we were to multiply our function by a factor of 4, that would vertically stretch it by a factor of 4. And if we were to multiply it by a factor of 1/4, that would be a vertical compression by a factor of 1/4. And again, we follow a similar pattern for our horizontal stretches and compressions. So let's just review the cube root parent function really quick. The cube root parent function is f of x equals the cubed root of x. And we could kind of explore this by making a table of values where all of our x's are perfect cubes. For example, the cube root of -8 is -2, because -2 times -2 times -2 equals -8. The cube root of -1 is -1, because -1 times -1 times -1 equals -1. The cube root of 0 is 0. The cube root of 1 is 1, and the cube root of 8 is 2. Okay, we've got some values. Let's graph them. So I've just got a simple little sketch here. And if I connect my points, I get a little graph that looks something like that. So let's talk about the domain of the cube root parent function. Well, are there any values where it wouldn't be defined? No, there are not. You can take the cube root of both positive and negative numbers, and you can take the cube root of 0. So what about the range? Well, in this case, since our domain is all real numbers, our range is also going to be all real numbers. So now that we've reviewed the basics of cube root functions and we've spent a little bit of time on the cube root parent function, let's take what we know about transformations and apply that to the graphs of cube root functions. So we've got an example here. Our first example is f of x equals the cube root of x minus 1 plus 3. And I've chosen some values here to check out. Before doing my table, I'm going to put a little thought into this and see what my a and b and h and k are. Let's see, I don't see any stretches or compressions here, so a is going to be 1 and so is b. We are subtracting 1 within the radicand inside there, so my h is going to be 1. And we're adding 3 outside the radicand, so my k is going to be 3. Now I can complete my table by substituting my x values into the function. So I've completed my table and now I'm ready to plot my points. There they are, so I can connect these now and arrive at something kind of like that. Of course, I should be going through that middle point there. Actually, that middle point is pretty important. That's HK. HK is the point of symmetry of the graph, and in this case, it occurs at the point 1, 3. So how is this graph related to the cube root parent function? Well, it's been translated 1 right and 3 up. Now let's look at another example. Why don't you pause the video and see if you can figure out this one for yourself? Hit play when you're ready to see the answer. So in this case, a is 2, which means we're going to have a vertical stretch by a factor of 2. B is 1 again. We don't have any horizontal stretches or compressions. Now I want to point out that h is -3. We have x plus 3, which means we're subtracting a -3. So h is -3. And then k is 0, because we're not adding anything outside of the radical. So I've substituted values, my x values, into my function to find some points that I'm ready to plot. Let's go ahead and make that graph. So my first point is a little bit off the area of the coordinate plane that I have, but that's okay. And I can see that the point -3, 0 is the point of symmetry for this graph. So how is this related to the cube root parent function? Well, it was vertically stretched by a factor of 2 and it was translated 3 to the left. I have one more problem for us to look at, and this is a real world application. This one is from our textbook and it's talking about an elephant. Specifically, it says the shoulder height h in centimeters of an elephant is modeled by the function h of t equals 62 1/10 multiplied by the cubed root of t plus 76, where t is the age in years of the elephant. So we can use this equation, this function right here, to predict how tall an elephant is going to be given its age. So I just have a table here, and what I want you to do is use a calculator to figure out the values of h of t for each of these numbers of years, and then plot that on the graph. See what you get. Go ahead and pause the video, do that, and then see what your graph looks like. So I've rounded my values, and now I'm ready to plot them. And there they are on the graph. I could connect it. It would look something like this. Of course, something to think about is we can't, and I didn't graph that perfectly, that's okay. We don't really have any negative values here because an elephant can't be less than 0 years old. And also, I want to think for a second, what does this value represent? Well, in this case, our y-intercept represents the height at birth. And that's 76 centimeters. That's the amount that we added, that's our k value. This graph has also been vertically stretched quite a bit. We've multiplied it by a factor of 62.1, which means that we stretched it vertically by a factor of 62 and 1/10. So that made it much more steep. One thing to observe is that as it goes on, it becomes less and less steep. And you can see that by looking at the table. The rate of change is definitely slowing down. So as the elephant gets older, it doesn't grow as quickly, and that makes sense. Can you imagine how tall people and animals would be if they grew at the same rate their entire lives that they grew at when they were babies? So let's write that down here, everything that we just talked about in this box. Can you infer any other information from the graph? Maybe you can. If you can, write it down in this box. So this is a real-world application of cube root functions.